Well, I guess I'll oh no, yeah. Oh, it's being recorded.
It's recorded, yeah.
Okay, cool.
Okay, so happy birthday again. And I think it's a pleasure to speak about, in this conference, about joint work with Zinovi and also with Ben Williams, which you can find in a paper on the archive. It's generating algebras via Versality. That's not the title of the paper, but that's the title of the talk. And throughout this talk, K is going to be field, if I don't say otherwise, and R is going to be some K-ring commutative K algebra of a finite type. Just means it's finitely generated as an algebra, and D will be the cruel dimension of R. And I'm going to repeat these notations a lot, so it's okay to forget them. And let me start with just saying what this talk is about. And the problem that I'm going to talk about is the following. So we're given an R algebra B, which is going to be finitely generated as a module. And we just want to bound what I call gen RB, which is just the minimal possible number of generators of B as an R algebra. And okay, this is a very general problem. And let me just give the starting point of this. The starting point of this is maybe the generate case where the product on B is 0, which just means that B is an R module. And there is a very old result of Forster, which says what happens in this case. So there is actually a way to bound the number of generators. This is from 1964, so it's very old. And it says the following. So let P be locally free R module of rank n, equivalently a projective module of rank n, then...
sorry, a very quick question. Is R supposed to have a unit?
Yes. Yeah, rings are unital, algebras need not.
Algebras are not. Okay, fine.
Yes, they don't even have to be associative, actually. But I in this talk, I will not consider non-associative examples.
The rings are commutative, but algebras
yes,
are not.
A ring equals commutative plus unital. Yes, always. Thank you. Then what Forster says is that the number of generators of P is at most n plus d, and let me remind you that d is the cruel dimension of R. So R does not even have to contain a field for this result. And I should say that Swan and Chase, well, Swan used an example by Chase, showed even before this result that this cannot be improved in general. And now I'm going to talk about more general algebras, and this is still too general, so we will have to arrange algebras into families. So how are we going to do that? We're going to introduce the following definition. So definition. So let A be a finite dimensional K algebra, not necessarily commutative, not even necessarily associative. So an R form of A, so R is R contains our field, is an R algebra B such that there exists some faithfully flat ring extension such that if I tensor A with S, this becomes isomorphic to B tensor S. So here I have to tensor over K, and here I tensor over R. This thing I often call AS. And this isomorphism is an isomorphism of S algebras. And this, of course, I should say that this implies that B is locally free as an R module because of descent. And let me give just a few examples because this recovers a lot of interesting families of algebras. And the first example perhaps is, let me do A equals K to the N with the zero product. So essentially no product. Then in this case, R forms are just locally free R modules of rank N. So in this case, we get locally free modules. So this is the first example. And let me do yet another example. What happens if we take A equals K to the N and we use the usual product, which is just the pointwise product? Then in this case, I should say, okay, let me say it's even interesting to consider K forms. So let me consider them first. Then they are known as étale K algebras. They're just the étale K algebras of dimension N. And étale algebras, so this is just a finite product of fields. And each of these is a separable finite dimensional field extension. So it's just an étale algebra over the field. Those are the K forms. And what are the R forms? The R forms are just the finite étale R algebras of rank N. So we get finite étale algebras. This is the second example. And perhaps a third example. Let us take the ring of matrices, S by S matrices. Then let me first say, what are the K forms? So K forms are just central simple algebras of degree S. This is one possible definition of central simple algebras of degree S. And in general, the R forms are what are known as Azumaya R algebras of degree S. And so each of these examples, I mean, these are important classes of algebras. I mean, at least the finite étale and the Azumaya algebras, they have their usages. This is not the place to elaborate on that, but you can actually continue this line of examples and define Octonian algebras over rings, and you can define Azumaya algebras with orthogonal involutions, symplectic involutions, etc. A lot of interesting families of algebras. But those are a few important examples of you can get in this manner. And now we can sort of modify, let's modify the problem. So modified problem. So let's fix a finite dimensional K algebra A. And the goal is to bound the number of generators of B when B is an R form of A in terms of the dimension, the cruel dimension of R, and maybe also some parameter depending on it. So that's a more specific problem. But before I will describe a solution or some solution, let me give some motivation, because at least there is some interesting geometry that hides in the background, and I kind of want to tell about it too. And why is it interesting to look at these things? And it connects to versality. So at least this is why I was attracted to this. And let us put G to be the automorphism scheme of A. So it's the scheme of K automorphisms of the finite dimensional algebra A. And there is a famous equivalence of categories. So apparently R forms of A, this category is equivalent to, I'm going to use left G torsors, E over the base R. So morphisms are isomorphisms of algebras or torsors. There's a categorical equivalence, and it is given explicitly by mapping a form into the scheme, the R scheme of homomorphisms of R algebras from B to AR, and this has an action, this has a right action by GR. This is a very famous equivalence. And so we're actually talking about, when we study forms, we're actually talking about torsors. And it turns out—
Sorry, that should probably be isomorphism rather than homomorphisms, right?
Thank you. Yes, thank you. Yes. So it turns out that there exists, so you can do the same thing, you can replace this ring with a scheme. And it turns out that there exists a scheme, a K scheme, XR. So here R is some natural number, and an XR form BR with distinguished generators. So this BR, so I'm working over a scheme, so they're going to be not exactly in BR, but rather in global sections of this. But you can pretend that this is an algebra, an actual algebra, which are universal. So it's not so trivial, but this is true. So they're universal for every form which is generated by R elements. So essentially every other R form which is generated by R elements is a specialization of this form, and the generators are specialized from these generators specifically. And let ER to XR be the corresponding G-torsor. Then we can actually rephrase our problem. So we can rephrase the problem as follows, and say that so we want to say that this ER to XR is this thing versal for G-torsors. So G-torsors E to X with X affine of dimension most deep. So what do I, or maybe I should even be more specific. I could say E to spec R. So R contains our field and of cruel dimension at most D. And you can sort of think of this diagram. So I have my E and I have my ER and XR. And this somehow corresponds to my BR over my XR. And this is in correspondence with B over R. And I want to have this kind of specialization. And this would mean, this would imply that this thing is R generated. And this would imply that this thing is R generated. So I want to have this property. So this is a kind of a versality question. So we can call, later I'm going to call such G-torsors diversal. But I'm going to give a precise definition later. And you can think, if you think about it, what Forster's theorem tells us, it means that there exist diversal GLN torsors. So Versality is typically for when this space is a field, right? When this base X is just the spectrum of a field. So here we're requiring to be the spectrum of something of dimension at most D, and a finite type over the field. So this is kind of the motivation that I had to deal with this, and the existence of such objects was foreshadowed in another work I had, and Forster's theorem kind of shows that they should exist, and they do exist. Okay, so after all this, let me move on to the main result. Any questions? Okay, so now I will have to assume that K is an infinite field. And R again is a commutative algebra of finite type.
So Forster's theorem by itself doesn't imply existence, right? You're saying the proof.
Yes, the existence is not trivial. The existence of such a universal example is non-trivial, and it should be proved as well. But in the case of modules, it's not so difficult. There is a generic projective module of rank n, which is generated by D plus an element. This is a construction of Michel Renan, and this was known. In general, it's not so trivial that such a thing should exist, and it is actually one of the results which I will tell you about.
No, I'm just saying that the statement of Forster's theorems.
It does not imply that. It does not imply that.
It's the proof that does.
I'm not sure even that. So I think maybe I should. So here I wrote this. So here I can say this plus existence of universal implies this. The existence of the universal thing object. Okay, let me continue. So again, D is going to be the Kroll dimension of R, which is also the transcendence degree in this case. And A is going to be some fixed K algebra of dimension N. And I will need to introduce, I'm going to have to consider the base change of A to the algebraic closure. And actually, oh, I need the automorphism group of A as well. Let me put it here. Quite a lot of notation. And I'm going to define N max to be the maximum dimension of a K of a proper K-bar subalgebra of A bar. So the largest possible dimension of a proper subalgebra. And theorem. So this is a joint with Zinovi. And Ben Williams. And under the previous assumptions, we have the following. So 1, let B be an R form of A, then number of generators of B is bounded from above by D, which is the Kroll dimension of R, divided by N minus N max. This is the dimension of N max is the dimension of a proper maximal dimension of a proper subalgebra of A. And there is another term here. I'm going to call it plus O of 1, but I will say that it is at most N max plus 1, and this can be made explicit. So this really depends on A, and this can be on A, and this can be computed, although it takes some work. And the second part of the theorem is assume assume the characteristic of K is 0 and G is not unipotent, then for every D greater than or equal to 0, there exists some K ring, and with with curl dimension of R equals D, and an R form B, such that the number of generators of B is at least, well, not as much as this thing, but a little less, D divided by 2n plus O of 1. So you need a number which is linear in the dimension. And here the O of 1 is less explicit. It depends again on A, and the requirement that G is not unipotent is essential, because otherwise we have no forms except a trivial one. And let me, okay, this is it's kind of abstract. Let me give some particular examples of this. So examples / corollaries. And first, let us consider the case where, well, let's try again the case where A is K to the n with the 0 product. And so B is just a locally free R module of rank n. And well, the maximum dimension of a submodule of A bar, well, this is just the maximum dimension of well, a vector space contained in K bar to the n. So it's just n minus 1. And then what the theorem tells us is that what we get is that the number of generators of B is at most D divided by n minus 1 plus O of 1. This O of 1 is at most n max plus 1. So here it's just n minus 1 plus 1. So it's less than or equal D plus n. And this is exactly Forster's theorem.
Can I ask a off-the-wall question, possibly? Suppose that you work in an analytic category and like you replace R by like a Stein manifold. Are analogs of these things known for like locally free sheaves of like OX manifold? Or do you know of any of this, like bounds on the number of generators?
I'm not. Most of this uses the fact that the base is affine a lot, so I don't know what happens if you try something which is not affine. And
well, that's why I want to replace it by a Stein manifold. I want to make it a Stein, like kind of Stein.
I don't know what is a Stein manifold. I'm sorry.
Yeah. Okay.
Okay.
Thanks.
This may be a problem to consider. Okay, so let me give a second example. So let's take A to the K to the n. So here B is just a finite étale R algebra of rank n, and the dimension of a maximal subalgebra is just n minus 1. It's very easy to see. And what we get is that the number of generators of B is at most D divided by n minus 1. So again, we have this O of 1, but here it turns out to be actually 1. You can compute that. This can be computed, and it turns out to be D plus 1. And I should say that works of Shukla and Williams from 2017, if I'm not mistaken, and independently by Oyanguren in an unpublished work, this is the best possible. Upper bound. So this bound is the best possible. There are examples which actually meet this bound, and you cannot do better than that. And let me again return to my third example from before. Let's take the algebra of S by S matrices. And here B is going to be an Azumaya algebra of degree S. And so what is n max in this case? this is not so trivial to find, but it is known. It's going to be the dimension of an algebra, which looks roughly like this. So it's a block upper triangular with the largest block possible. The dimension of this is s squared minus s minus 1. So what we're going to get is that the number of generators of B is less than or equal to, so here, now we get something more interesting, sublinear, I'm sorry, less than the constant function. We're going to get this, and then there's the mysterious O of 1, which now turns out to be just 2. And this is going to be D divided by S minus 1 plus 2. And I should say that you can ask if this upper bound is tight. And in the same paper, this is, I should say, mostly a result of Ben. So I'm highlighting his name more, of Ben Williams. I hope it's okay. There, for every D positive and every S, at least 3, there exists R of Kroll dimension D and B over R Azumaya of degree S, such that the number of generators is not exactly that, but almost that, up to a factor of 2. So there is some discrepancy. So here we have a 2 appearing. You do need a lot of generators sometimes. And okay, how much time do I have? Okay, I want to say something about kind of the history of this result. It's a very recent history, but I want to say a little about how it came to be, because I think it's interesting. And I should say, okay, so the main theorem, I went to a honeymoon in Vancouver, and on that honeymoon, there was one afternoon which was academic, so it was not really a honeymoon. So my wife went to a museum, and I went to visit UBC, and I met with Zinovi, and for I think 2 hours, and then I gave a talk, and that was the mathematical part of the honeymoon. And from that came actually this paper, what eventually became this paper from that discussion, I think. So that is one thing I wanted to say. And the second thing I wanted to say, okay, let me make some history. There was another earlier result, and maybe some of you, I think I gave some talks about it. So there's like I don't know, theorem, let me call this theorem B. So this is in a very short paper, and this is from an earlier in the Compte Rendu, and it says the following. So let R be any Noetherian ring, not necessarily containing a field. So I'm going to take D to be the Kroll dimension of R as usual. Well, no, I can actually take it to be, D is going to be the dimension of the maximal spectrum, which might be smaller. Let B be any finite R algebra. So not necessarily a form of something. And suppose that for every maximal ideal, the number of generators of R over M over R of B over a tensor B with R over M, I tensor it with the residue field, and the number of generators is at most N. Then the number of generators of B is at most N plus D, or D plus N, I guess, where D is the dimension of the maximal spectrum. And for instance, you might think, okay, so when B is Azumaya, so what you get is that the number of generators of B is at most the number of generators of a central simple algebra over its center plus D. Well, this is a folklore fact, which is actually recovered by this result. This thing is always 2. It relates to this 2. So it's d plus 2. And we were curious if this is optimal. And I mean, we had similar bounds. You get the d plus 1 for étale, you get Forster's result from this. And we asked Ben Williams, and he constructed examples requiring this many generators. Where S is the degree of B. And we were, so that we have this and we have this, and we were kind of baffled by the significant discrepancy here. And it turns out that the main theorem actually improves this bound. And so this was a kind of it almost meets this up to a factor of 2. And so this is kind of resolved it. And maybe I should say that so you can have a corollary to the main to theorem B. You can actually show the following. So if R contains an infinite field K and A is a finite dimensional K algebra. And okay, so let's say that the D is the dimension of the maximal spectrum of R. And so then for every R form B of A, we have the following formula. You can you can show that this is a corollary of the theorem. You get D plus the number of generators of A is a K algebra. And what the main theorem says is that you get something similar, but you get slightly less. You get D divided by N minus N max plus O of 1. So this is a little better. But R must be of a finite type over K. So that is one difference, and the other one is that you can take the dimension of the maximal spectrum. So we don't know if if this can be improved. You said there's a problem session, so here is one possible problem. Any questions so far? Okay, so what I would like to do in the remainder of the talk is to tell you a little about the proof. And this is I said that versality is involved. So I will explain precisely how. Okay, so let me recall. So we have A is a finite dimensional K algebra, and G is the automorphism scheme of A. I should say that essentially this generality G doesn't have to be smooth. And I should say that by results of Gordiev and Popov and by Milne, so they did it in the zero. This is the characteristic zero case, and this is the positive characteristic case. Essentially, all algebraic groups can occur here if the field is large enough, including the non-smooth ones. And also recall that for K scheme X, we have an equivalence between X forms of A and again left G torsors E to X. And what I want to do now is to construct the universal R generated form. So here is a construction. It's not so trivial that it has the required properties, but it does. So let us fix some natural number, and we're going to define the following schemes. So VR is going to be A to the R, regarded as an affine K-space. And if you want to be more precise, it's actually convenient to think the S points of VR are going to be AS to the R, where S is any commutative unital K algebra, and AS is, of course, a tensor S. And this is VR, and I'm going to define an open subscheme. So this is going to be an open subscheme of VR, which is determined as follows. So I'm going to tell you what are the S points, and the S points are going to be just R tuples in AS, which generate AS as an S algebra. So if you want to be more precise, so this is just A1 to AR in AS to the R, subject to the condition that S is the algebra generated by all of these guys. So here it's as an S algebra. So I gave you the functor of points. It's not so trivial. It can be checked that this is indeed an open subscheme of this. And finally, I'm going to consider the complement, which I call ZR, and this is going to be a closed subvariety of a VR. I'm giving it the reduced induced subscheme structure. Okay, so and notice that G acts on VR and UR via the following action. So it's a left action, which is why I'm using left torsors. If I can apply an element of the group to a tuple of generators by just applying it to each member of the tuple. If these generate the algebra, let's say I work with here with the S points, if they generate AS, then these also generate AS because G is an automorphism of the algebra. And so it acts on there. I should say there you should be careful. It doesn't actually act on ZR because G does not have to be reduced, but we don't need the action on ZR. Okay, so I can the action of G on UR is free, so no stabilizers. Stabilizers vanish. So this means that I can form XR. I can form the quotient. This is doesn't have to be a scheme. It's an algebraic space. It is a scheme if G is reductive, but we don't know in general. And UR to XR is a G torsor, and it corresponds. There's a corresponding R form. Let me call it BR, and this is the universal. This corresponds to an not R form, sorry, an XR form. And here is a proposition which I will not prove, but I will say informally it means that this BR over XR is the universal R generated form of our original algebra A. This is an informal way to put it, but let me give a more precise and more useful statement. Let E to spec R be a G torsor corresponding to an R form B. There is a one-to-one correspondence between the following two things. So one, tuples B1 to be R ordered tuples, I should say, generating B is an R algebra. And the second is pullback diagrams as follows. So I have E and I have my spec R, and here I have my UR and XR, and I'm going to have having such diagrams where this thing is a G equivariant, and this is a pullback. And I should say the top arrow actually determines the bottom arrow if it exists. And so we actually have, so the question is now, does this thing specializes to any torsor of this form with some dimension restriction on R? And okay, maybe I should say here in particular, B is, well, the number of generators of B is at most R if and only if exists a G equivariant morphisms from E to UR. So we really have to, so this is a versality question in a sense. And okay, so let's make that into a definition, into a precise definition. And let me say that a G torsor, so here the base is an algebraic space, but let me allow such a situation. So a G torsor E to X is called, and really it's weakly diversal, but we don't have a good notion of what versal or strongly versal should be. We don't know yet. It's called weakly diversal if for every G torsor E prime to X prime with X prime affine of dimension of finite type over K and the dimension of X at most D, there exists specialization as follows. So we have E prime to X prime, E to X, and we want something like this to exist. And this is, of course, a G equivariant.
I think you want the dimension of X prime to be at most D.
Thank you. Yes, this is X prime. Yes. So we want to show that this universal R-generated form is diversal. So, okay, so how are we going to, how can you prove such a thing? So notice, so okay, let me state this goal. So the goal is now to prove that this torsor UR to XR is diversal for some D. And something to note here is that UR is VR minus ZR. So this is the scheme of generators, and this is the scheme of all tuples of elements, and this is the scheme of non-generators, if you want. And VR is a representation of G. And there is a famous result that if you take a representation of a faithful representation of a group and you remove the locus where it does not act freely, you need to remove a bit more, then the quotient is going to be versal in the classical sense. Then turns out that this can be improved, and if the codimension of this ZR is large enough, then you will get something which is diversal. So this is last theorem for today. So let rho from G to the endomorphism of V be an algebraic representation of G. Let Z be some closed subvariety such that V minus Z is stable under G, and G acts freely on V minus Z. The quotient might be an algebraic space. I'm not too worried about that. And let us put D equals the dimension of V minus the dimension of Z minus 1. Then V minus Z to the quotient, which is a G torsor, is D versal. And I should say that it is well known that this is strongly versal. So every torsor over a field is a specialization of this. But it turns out that if the codimension here is large enough, then it's actually D versal. So let's kind of wrap it up. So now all we need to do is to take V equals VR and Z equals ZR. So the dimension of V is R times the dimension of A as a K algebra. This is just R times N, the dimension, N was the dimension of A. So what we get is the following corollary, is that UR to XR is D versal if D is smaller than Rn, which is the dimension of VR minus the dimension of ZR. So now it remains to compute the dimension of ZR, but here is another maybe a corollary. Corollary 2 is that if D is less than or equal less than Rn minus the dimension of ZR, then every R form is generated. Okay, every R form D is with R. Let's say that D is the Krull dimension of R, is generated by R elements. So this is what we get, and you can actually show. Okay, so one can show that, okay, the dimension of this ZR, okay, so it's this is let me remind that this is sort of the variety of R tuples not generating A. So an N max was the dimension of a proper subalgebra, the maximal possible dimension of a proper subalgebra. So this will be at least N max times R. And it turns, because you can choose the R tuple to be in the maximal subalgebra, and it will not generate. And it turns out that it's not too far from this. This is, you can actually, you get this, I'm sorry, you get this upper bound. So it's not too far from this. This is a constant where N is the dimension of A. This is the dimension of A. And this together, this gives the main theorem. So if you use this together with corollary 2, this together, it gives the main theorem. And all the more precise bounds, they told you that the O of 1 kind of hides in this thing. It hides here, and you need to compute it. Okay, I have 1 more minute, so I actually want. So I know there is a problem session, but I have a few questions. I have a question which I want to, make. I hope that is fine. I have a few questions about to ask, and the first, well, maybe the main one is okay. So the first one is the main result holds if R contains a field and R of a finite type over K. So it contains a field. Oh, and it contains an infinite field. It's important. So what if we drop these assumptions? So in particular, the case of finite fields is very interesting because the results are actually not true, but you can bound it nevertheless in some cases, because we have the theorem D, which worked over any ring. And maybe another question is there a good definition for, I don't know, strongly diversal G-torsors? So is there a good definition for this? And let me even speculate. So I have a kind of a speculation or an expectation, and which is that if E to X is strongly versal G-torsor, then it should manifest then. I think that there is a map from the Cho ring of PG of the classifying stack to the Cho ring of X. And so it should be an isomorphism if I is less than D, because we have such an abundance of maps from torsors over D-dimensional things into X, then I would expect that any rational equivalence could be exhibited on X if it's a flow dimension. I don't know. So this might be a good notion. So this is another question. That is it. Thank you.
Thank you. So I'll open it up to the floor to any questions for Uriya.
I just wanted to say that Google kind of said yes to my question about Stein manifolds. I can share the paper, but what they say, there's a paper of this guy Kripke, and he says that if you have a vector bundle on a d-dimensional, basically d-dimensional Stein manifold is n-dimensional vector bundle, then is generated by n times d plus 1 of its global sections. Does that mesh with the
bound which we had was n plus d, so you can.
So that's a way bigger bound. Like they need way more.
Yes. Yes. Yeah. So there is a big discrepancy.
Yeah. Okay. Oh, so that bound is n plus d just for, in the case of the algebra that corresponds to the vector bundles is just the trivial product.
Yeah, it's the zero product. You can ignore the product. You're not allowed to use the product to generate, in some sense. It's a multi-algebra with no operations. That's the correct way to think of it.
So for Stein manifolds, I think it's kind of a topological question, but is there a topological analog of this thing, like in purely?
Yeah, for lower bounds, Ben Williams actually proved them in the topological setting. He's here, maybe he can say something about that. So I think that probably covers your setting of Stein manifolds. It didn't make it into our paper though.
Yeah, okay.
Ben, are you there?
I'm sorry I didn't speak about the lower bounds. We're limited.
Oh, we can't. Yeah.
He cannot unmute.
Yeah. Oh, it's no big deal. I mean, yeah.
Well, anyway.
Okay. I should say that sorry.
Go ahead. No. I was cutting you
off. No,
off.
I said the theorem B, the earlier theorem, there is a very different proof of it. The one which does not require the ring to contain a field. And I think that proof actually works for schemes, and it gives you sections which are not necessarily globally defined, but still generate the algebra. But the idea of the proof may turn out to be relevant. I don't know. It's a very different proof.
Cool. There any other questions? So I had one. So you sort of answered it a little bit with your other question, but so should I think of? I know this is informal because you don't have a proper definition yet, but you should somehow be thinking about these d-versal torsors as like zero versal is the ordinary versal, and it captures only like the birational information. And then somehow you're saying that by demanding D to be higher, you're demanding that your torsor captures higher dimensional information.
I guess so. I should say that we only do things of finite type, or maybe finite transcendence degree. In the paper, it's finite transcendence degree, I should say. So it's not trivial to go to schemes which are not of finite type, even if the Krull dimension is finite.
Interesting. Any other questions? Okay, well, let's thank Uriya again. So our next talk is in 20 minutes, whatever your time zone is, and it'll be Sasha Merkuryev, who I believe is already here. Thank you.
Thank you.
Great talk.
Thank you.
Thank you very much. I enjoyed it.
Yeah, I like that. I like that you can take screenshots of talks. So I now have your definition of versality hidden away on my.
I didn't know that you could do that.
Yeah. Well, yeah. Well, not with Zoom, but with your computer anyway.
Actually, do you still need the board? This is still recording, by the way.